most of you guys did very well on the exam. So you did a great job. You know, most of you guys took advantage of being able to take it a second time. So that certainly helped quite a bit. But I want to go back over it just because there are a few issues there. There's a few places where I noticed kind of consistent issues with people giving the same answers, maybe something I didn't make clear, or maybe something that, I don't know, just got mixed up in the translation or something like that. So I just want to go over those. We'll run through these questions and answers very quickly. Anybody have a particular problem? If you have a particular problem that you're concerned about, I'll jump right to it. Otherwise, I'll just go through them in sequence. So you can type into the chat box if something like that exists. And this will get you a view behind the curtain here as well. Okay, as sampling size increases, all else is held constant. What happens to the standard error of the sample means and the width of the confidence interval? Well, let's see, the confidence interval is equal to X bar plus or minus the standard error, right? And the standard error is equal to sigma, standard deviation of the population, over the square root of the sample size. And the confidence interval gets wider, right? The width of the confidence interval gets wider when that margin of error, that 1.96 or that t-score times the standard error gets bigger. And that gets bigger when the sample size gets larger, when sample size gets smaller, and when sigma gets bigger, right? When it makes that equation bigger. So standard error and the width of the confidence interval both decrease as the sample size increases. Sample size goes up, that standard error decreases, sigma over the square root of n, bigger n, smaller sigma, smaller fraction, which is sigma over the square root of n. And since you're subtracting and adding that to the X bar for the confidence interval, as one gets smaller, the confidence interval gets smaller too. As the standard error gets smaller, the confidence interval gets smaller as well. I think almost everybody got that right. Okay, let's see. Which of the following is true about a 95% confidence interval? And this one, you have little square boxes. It means you can select more than one option. In this case, there were two right options. Provide a range. 95% confidence interval provides a range within 95% confidence that the true population mean resides. And that also means that if we took 20 samples of the same size, then it's likely, because we're going to be right 95% of the time, that 19% will capture the true population mean. In one case, the confidence interval, it's likely the confidence interval will not capture it. The true population mean will be outside of the confidence interval. We can be more sure of that by going to a 99% confidence interval, which is a wider interval, makes it more likely that we're going to capture the confidence interval. What about these other two? Accounts for bias in the calculation of the mean. No, it doesn't do that. It only counts for chance, right? Only counts for the way that chance affects our sample collection, but not bias, not, for instance, a situation where you might have a confounding factor, like one group has a lot of smokers, the other one doesn't, and so on. And 95% of the population values are within the confidence interval. That's not true. It sounds good, but it's not true, because really all that the confidence interval represents is the probability that is 95% that the true mean lies between there. The actual population is a much wider range than that. Okay, that's your standard deviation and for the population, sigma for the population. Okay, check all that are true. Check all that are true about the t distribution. Just like the z distribution, the t distribution is symmetrical around 0. Okay, the standard t distribution. It has wider tails than the standard normal distribution. Well, we know that because in order to get our 95% confidence interval when we use t, we have to go further out because the tails are wider. It must be used when the population standard deviation is known. That's not true. We don't need to use it when the standard deviation of the population is known. We can just simply fall back on the z-score, 1.96, 2.58, and so on and so forth. So the only time you really need to use the t distribution is when the population standard deviation is not known. the opposite of that. When using the t-distribution, we assume that samples are drawn from an approximately normally distributed population. That's true also. We typically want an approximately normally distributed population. We're less dependent on that as the sample size gets larger and larger and larger. Okay, and as we would expect, the t-value for a 95% confidence interval gets smaller, it gets smaller and smaller and smaller, getting closer and closer and closer to 1.96, but it doesn't reach 1.96 until you reach the full population, okay, or infinity. The t-distribution can be used for large or small sample sizes. Yet you can use it. In fact, SPSS always uses the t-distribution, okay, for all calculations. The p-value is probability of obtaining a sample as at least as extreme as the one you observed if the null hypothesis is true. And that's exactly right. The significance or p-value that you calculate or that you get from SPSS is the probability that you would get that big a difference between the value you would expect and that sample that you got. Okay, the probability you would get that extreme a value if the null hypothesis were true. In other words, your sample is drawn from the same population as the number that you're comparing it to. So that is true. That is true. That's what the p-value represents. Since we're willing to take up to a 5% chance of being wrong when we say we reject the null hypothesis, well, that p-value, if it's smaller than 5%, in other words, we'd only expect to get that 5%, less than 5% of the time, if the null hypothesis were true, well, that we're willing to take that chance and reject the null hypothesis. If it's not 5%, if it's 6 or 10 or 15%, we're not willing to take that big a chance, so we fail to reject the null hypothesis. Too big a likelihood of getting that result if the null hypothesis is true. Okay, so p-value similar to or larger than similar or larger when using an estimated when estimated using a t-distribution than when using the z-distribution. P-values are similar or larger. If the sample size is big, they're similar to the z-distribution. If the sample size is smaller, they can be quite different than the z-distribution. In fact, but they'll always be larger, so that's true. Okay, when standard deviation is estimated from a sample, which distribution is more appropriate for hypothesis testing and confidence interval estimation? The t-distribution, always the better choice. Okay, we do allow, when you have a very large sample size, for convenience, if you want to do a quick calculation, to use the z-value, but that's only for a very large sample size and to estimate it. Again, SPSS always uses the t-distribution when you're determining a sample. The confidence interval for the mean seeks to capture the population mean. Of course, that's what we're after, right? We're not after the sample mean. We got the sample mean as soon as we got taken the sample, so that's not a good. That's not what we're really concerned about. The standard deviation of the population, it might be interesting, but what we're really after is the population mean when we determine the confidence interval. Okay, so we're looking to see within which range that population mean resides. Using a table of t-distribution with 10 degrees of freedom, and that would be a sample size of 11, right? To determine the values of t, capture the 95%, middle 95% of the area under the curve. These values of t are, and you would go to the t-distribution table, and you would look up the values for t that represent 95%. Okay, so with a small sample size like that, these numbers are going to be bigger than 1.96. And in fact, in this case, they are negative 2.228 and positive 2.228. Right? Either way, could be bigger, could be negative or positive. It's really the magnitude that's important there. These are way too big. They're a little bit too big, and these are too big as well. Okay, you guys are okay with looking that up on the t-table, right? Should I pull a t-table up? Let's pull a t-table up. Just check that. I think I have a t-table. Okay, let's see. That's not it. Here we go. That's it. Okay, 11 degrees of freedom. Okay, 95% confidence interval, 2.201. Whoops, 10 degrees of freedom. 2.228, that's where we get our 2.228. And since that could be either on the left side of the distribution or the right side of the distribution, the right tail probability, okay, is shown here, then it would be negative or positive. Anything beyond that, negative or positive. Okay, let's go back here. Okay, so now a lot of people got this wrong, I think. Oh, no, I'm wrong. Okay, was this a tricky one? There's one tricky one in here. The next one's tricky. Okay. National Health and Nutrition Examination Survey and Haynes assesses the health and nutrition of adults and children. 712 men from the ages of 20 to 29 were examined. The mean body weight in this sample was 183 pounds. The margin of error associated with this estimate for 95% confidence was plus or minus 3 pounds. What is the probability expresses a percent that the true population mean weight of men between 20 and 29 is between 180 and 186 pounds? Well, the mean body weight was 183, so our margin of error, which includes our standard error and our t-score for our sample, which is going to be very close to 1.96, because look how big that sample is, right, is 3 pounds. So our confidence interval, remember, this is not the standard error, this is our entire margin of error. So our 95% confidence interval is 183 minus 3 and plus 3, which would be our 180 to 186. So that's our 95% confidence interval. Okay, now this is an interesting one. I got almost, I would say probably 90% of the class chose it's impossible to tell from the information given, right? Okay, so let's take a closer look at that. Okay, so assuming that the weights, that's the same 95%, 3 plus 1. Assuming that the weights are normally distributed, what percent of individuals weigh between 180 and 186 pounds? Okay, let's take a look at this. Okay. So we know this is upside down. That's why I can't write on it. Okay, so we know that the mean of our sample is 183. We know that our margin of error is equal to 3. Okay, that's how we got 180 minus 3 and 183 minus 3 and 183 plus 3 is our confidence interval, 180 to 186. Okay, so now we're interested in knowing what percentage of the, margin of error, what percentage of the individual in its population weigh between 180 and 186. Well, we got a confidence interval, but that's not what we're asked for here. Okay, so what I need to know, I know that the mean is 183. I know the confidence interval is this, but now I really need, in order to calculate what percentage of the population, now this is the population, what percentage of the population is between 180 and 186. I need to know how many standard deviations that is. In order to know that, I need to know what sigma is. I need to have an estimate of what sigma is, right? What standard deviation is of the population, not of the sample, but of the population. So let me see, I know a formula here. The standard error is equal to, let's see, what's it equal to? It's equal to sigma over the square root of the sample size, right? Okay, so the standard error over the square root of the sample size. So what do I know here? I know the margin of error is equal to 3, right? So what's the margin of error equal to? The margin of error is equal to, let me see if I can do this without messing it up. It's equal to 1.96, right? Pretty close to 1.96 times, and as a matter of fact, you know what I'm going to do? I'm going to make that 2, because look how far apart these things are. It's equal to 2 times the standard error. Well, wait a second, the margin of error then is equal to 2 times the standard deviation over the square root of the sample size. Okay, good. So the margin of error was equal to 3, right? Well, that means that sigma over the square root of the sample size is equal to 3 over 2 is equal to sigma over the square root of the sample size, which was 712. Do I even need that? Okay, I think I do. Okay, so what do I have there? So if I multiply by the square root of 712, right, square root of 712. Okay, if I work that out, so 712, take the square root of that, is that times 3 equals, divided by 2 equals, so sigma is equal to 40. The standard deviation is equal to 40. Okay, so standard deviation is equal to 40. So now I know the standard deviation. Standard deviation is equal to 40. And I am looking for 3 below 180, a mean of 183, and a value of 186. So how many standard deviations below is 180? Well, it's going to be, or above is 186. That's true 186. So 186 minus 183 over 40, our standard deviation. The z-score for that is going to be 3 over 40, which is equal to, let's see, clear, 3 divided by 40 is equal to 0.075. So the z-score here is plus 0.075, and the z-score here is minus 0.075. So I'm going to go to my z-table now. See if we can find my z-table. Okay, minus 0.075. 0.075 is, looks like it's about minus 0.075. Looks like it's about somewhere in here. I'm going to say 0.47. Right, so this area from that z-score down is 0.47. So this area in here is 0.03. It's 3%. Right? Well, these two are symmetrical, right? I mean, this is the same z-score below the mean as above the mean. So this is 0.03. So the population itself, 6% of the population is between 180 pounds and 186 pounds. Thank you, Cindy. So that's how we figure out, we work our way backwards. In other words, we knew that our margin of error, think of it this way, we knew our margin of error was equal to 3, but it's also equal to 1.96 times, roughly 1.96, times sigma over the square root of n. Well, we knew what n was, that was 712, so we only have one unknown here. The only unknown we have is sigma, the population standard deviation. So if we know the population mean and the population standard deviation, which we figured out just by substituting what we knew in that formula, we can use that to determine what percentage of the population is between 180 and 186. See, once you get that sigma, you're just dealing with the same kind of standard deviation problem we started the semester with. Okay, so was that problem a dirty trick, or was it a dirty trick? Okay, yeah, okay. Well, it's only a few points, and I think I made it extra. Yeah, exactly. Oh, by the way, I think the exam adds up to 103 or something like that, plus the 4 extra points. So to balance it out with the other exam, I'm going to be dividing it so it's really 0 to 100. So if you see it drop a half a point, don't freak out. That's the reason, okay? So, but if you got that one right, I'll add in the extra 4 points. But I think at least one person got it right, I think. Very tricky. But you understand, see, that's the nice thing about this. It makes you think about the problem a little bit, what you know and what you don't know, and how you can apply those formulas. Okay, so let's move on. And I hope I still got this open. Okay. Actually, I can make this appear also so that you guys can see it as well. I can show you the feedback on some of these things I've already put in feedback, so you can see the feedback. You don't see it when you're taking the test, though. Okay, for a given population, to cut the size of the 95% confidence interval in half. Okay, what do we need to do to cut the confidence interval in half? Well, what reduces the confidence interval? The sample size, that margin of error. So in order to cut it in half, we have to increase the sample size. Now, if the standard error was only equal to sigma over n, then all we had to do was divide the sample size in half. But it's sigma over the square root of n. So in order to get that n part, the denominator part, to be twice as large, we need to increase the sample size 4 times, right? Quadruple it, because when we take square root of it, then it's double, right? And that halves that margin of error, okay? And consequently also the confidence interval. So that's quadruple the sample size. And again, it's a little bit of a test of your understanding of how that formula works. Delays in discharge from an intermediate healthcare facility create unnecessary risks. Discharge delays and days were recorded for 2 healthcare facilities. I kind of put these in a little bit backwards, because I gave you the independent samples t-test first, and then the single sample t-test afterwards. But I think most of you guys were able to figure that out. Okay, so in order to compare the delay times using a t-test, which assumptions are required? The data represents statistically random samples from their respective populations. Yep. Delay times demonstrate no major departments from normality. Okay, we want it to be roughly normal. Okay, and the 2 samples are independent. Okay, in other words, they aren't like from this. They're not just relatives of each other or taken from people that work from the same company or something like that. They're truly independent and randomly sampled. And in fact, all of the above, because those are our 3 primary requirements for assumptions that we have for the t-test. I think if you went back on one of the slides or one of the lectures, we would have said these are the assumptions for a t-test. Okay, that's why all of the above. And once you figured out that at least 2 of them were, then pretty clear that it's all of the above is the right answer. Okay, now, which is the appropriate null and alternative hypothesis? Almost everybody got this right. The mean for group 1 is equal to the mean for group 2. Alternative hypothesis, the mean for group 1 is not equal to the mean for group 2. Okay, now, 2 things about that you should recognize. One is that notice that we use mu. We didn't use x bar, we used mu because the hypothesis always deals with the population, not x bar. Right? In other words, x bar is our sample, but our hypothesis is that the means for the populations are the same or different, not our samples. We know what our samples are. What we're always wondering about is our populations. Okay, so then we have this. We actually have this in this file available in SPSS, and we can open it in SPSS. I have it back here. I'm going to open it up. Okay, let me get to desktop. And I think it's discharge.sav. Yep. Okay, we'll wait for SPSS to open up for a second. Okay, we're comparing facility A and facility B. Okay, here we go. Here's we opened up in the variable view. One variable is the number of days of delay, and the other variable is the facility. Facility is a nominal variable, and the delay is a numerical variable. If I click in there, I can see one represents facility A and two represents facility B. If I go to the data view, we can actually see this data. If I turn on the cooperative view and I turn on the value labels, you can actually see it's substituting for A and B with the facility name. Okay, so now we want to do our teach. We want to compare the means of these two samples, X bar 1 to X bar 2, as a means of testing our null hypothesis that the true population mean for facility A is equal to the true population mean for facility B. And these are based on these delays. Analyze. We're going to go to compare means to independent samples t-test. Okay. Now we're going to find the test variable, what we're going to find the t-test for, the means, the average of the means and t-test for is our numerical variable, which is the number of days of delay. And then we're going to group it according to facility. We're actually comparing the facilities. Okay. And it asks me to identify what the numbers are that represent the two facilities. So it's convenient for me to open up in the variable view there. I'm going to click OK. So output table opens up, and we can see first here we had 12 people in each 12 facilities in each group. The mean of one was 13, the mean of the other was 11. The samples are different. Real question is, do we have enough evidence to say that the population means all of the delays all of the delays for several years, let's say, for the facilities were different, were the same or different. So we have standard deviation. Those standard deviations are very close to one another. So it looks like we're going to assume that the variances are equal for these two groups, right? Remember we said that unless one is double the other, we're probably going to assume equal variances. Okay, so it's a little tough to see this. I'm going to read it. Okay, and there's a line over here, comes down from the end, that's vertical, which tells me, whoops, sorry, let me get this out of the way, comes down from the end and separates the t-test and this Levene's test for equality of variances. The top line assumes equal variances. The bottom line assumes, it says that equal variances are not assumed. Okay, and there's a statistic, they call it an F statistic. They tend to use F for a lot of statistics in these tests. And the significance or p-value or probability of a null hypothesis. We'll talk about which one being true. And then from this line to the right is our t-test. So we have to decide, do we want to use the bottom row or the top row? And as we said, just looking at this, we most likely are going to choose equal variances assumed. But I'm going to go down here. See, so I'm going to use this just like the null hypothesis. My null hypothesis is that the variances are equal, and unless the significance is less than 0.05, in other words, that the differences are so extreme that I have less than 5% chance of being wrong if I choose not equal variances, well, I'm going to stick with that top line then. And in fact, the significance is 0.61, much bigger than 0.05. And it goes along with these numbers for standard deviation being very close together. So we're going to stick with the top line. Top line tells us the t-value for this test is 1.528. The degrees of freedom is 22. And the significance is 0.141. Okay, since there's a 14% chance we would get this big a difference, a mean of 13 in one sample and 11, the X bar 1 is 13, X bar 2 is 11. That there's 13% chance of getting that big a difference, even if the null hypothesis were true. That means we fail to reject the null hypothesis. We need that percentage, that probability to be less than 5%. Okay, so let's see what we have here. Hopefully these numbers will match. And here we have 1.58. They gave you a range of 0.1. So if you put 1.428 to 1.628, you got marked right on that. And with the null hypothesis, we rejected at an error rate of 0.05. And the answer to that is no, because it's way too low. Okay, so the next example, is a single sample t-test. Now, I don't think I gave you a file for this, right? I may have put one up late after somebody complained or something like that, but I don't think I did. The intention here was that you could either do this in Excel, or you could just copy this into SPSS. Let's see if I can do it here. Okay. Okay, and these are temperatures for a, what do they call the group here? We have blood donors. These temperatures, they take blood donors' temperatures these days because you don't want someone that has an infection, raging infection of some kind, to be donating blood that day, so they take their temperature. What we're examining here is whether or not the temperatures of these blood donors is significantly different than the general population, which suppose somebody says is 98.6. I don't know if that's really true or not. That's kind of like, that's Dr. Google says it's 98.6. I don't know. I'm sure there's been studies done, and that's probably an old saw, that, like, who knows if anybody's checked it in the last century. So at any rate, so we're assuming that the general population is 98.6. In other words, we're comparing our sample mean for our sample population from our special population, the blood donors. We're comparing that to a known mean. So there's only one sample that we've collected here, only the donors, and we're comparing it to what we believe is the true mean for the general population, 98.6. So there's a couple of ways that you could state this null hypothesis. One could be just the mean. Remember, now this is mu. Mu for the donor population is equal to mu for the general population. Or you could just say mu is equal to 98.6 because you know mu for the general population, right? You know that is what mu for the general population is. You can just substitute it. You cannot substitute 99.1 for the sample population because that's X bar. It's not mu, it's just X bar. And you can't write 98.6, 99.1 is equal to 98.6, and 99.1 is not equal to 90, because you need to use mu. You need to identify the sample population, the donor population. Okay, so anything that has 99, that mentions 99.1, which is the sample, X bar, not mu at all for the donor population, is a problem. And anything that equates them, puts X bar in there instead of mu, is a problem as well. Okay? Okay, so that shouldn't have been tricky, I don't think. So let's actually go ahead and do this. Let's see if I still got SPSS open. Well, yeah, I do. Okay. I'm going to create a new file in SPSS. And I'm going to just click in there and say Control V. And there's all the numbers. SPS. All I did was click in the first one and say Control V, and it dropped them in there just to do the same thing from Excel too. Okay, so now I'm not going to, notice it gave it a default variable name. You could go into the variable view and you could tell SPSS that this is a scalar variable and that the name, that this variable, let's name it, dtemp. And under labels, call it donor temperature. Okay, so we can clean things up a little bit there. I'm going to go back to the data view. I'm going to go to Analyze, Compare Means, except this time only a single sample was taken, right? So it's a one sample t-test. And I'm going to say, okay, so the only thing I've taken a sample is the temperatures. I missed the T there somewhere or other. Temperatures of the donors, dtemp, right? And what am I comparing it to? I'm comparing it to the test value of 98.6, the general population. The other group where I know the population. I'll click OK, and it'll calculate our t-value. And our t-value, the mean came out to be 99.6. I'm not sure I got all the values in there, to tell you the truth. And the t-value was 2.747 with a significance of 0.02, less than 0.05. Notice we only get one line here because there's not two groups to decide whether the variances are equal or not. So let me see if that's right. because it may not be right because I'm not sure I got all of the values in there when I copied and pasted it. Is it the same as we have here? 90 and 90. Standard error. Well, actually, since you asked calculate standard, well, I think it gives you, did it give you the standard error in the SPSS output?
I did Excel.
Yeah, I think most of you guys just used Excel. Once you saw it was a single, and it was a relatively easy calculation. I think most of you guys stuck with Excel. Let me see if they give you the, yeah, it gives you the standard error as well. So you could have saved a little bit. Actually, the really smart thing would have been to use Excel, but then use SPSS to check your work. Okay, and there we go. Okay, so that's about the same. The value of t, 2.47. The critical value for t for this sample size. The sample size was 10, I believe. So degrees of freedom is 9. So we go to our t table and look it up, and it will come out to be 2.262. I think it's the same one we used before. And so did we exceed that value? Well, in SPSS, you could just look at the significance and know we could reject the null hypothesis. Here, you would have to compare this to our value of 2.747. Our value exceeds the critical value of t, so we can reject the null hypothesis, just like having 5%. Okay, let's see. We reject the null hypothesis. Good. Okay. 550 out of 1,000 randomly selected New Yorkers believe Mayor de Blasio's vision. This has been under a lot of stress here lately. His vision 0, right, with the bicycles and stuff like that. You know, his traffic safety program lately has been getting a black eye because of all the bicyclists getting run over. And I don't know if any of you guys are on any of these bulletin boards or Facebook or something like that, where you have friends that are bicyclists, but they're getting militant bicyclists. They're getting crazy, yeah. And between me and you, I mean, I understand, but this city is really not really designed well for bicycles, and it's not designed well for bicycles and cars to occupy the same space. Now, I do a lot of driving, and let me tell you, just yesterday, at least 3 bicyclists just flew across in front of me, not even looking when I was crossing the intersection with a green light. One guy must have been like 70. Didn't even look up, nothing, just got completely. But yeah, so, you know, and then the others driving the wrong direction and on the streets and stuff like that. Don't drive the wrong direction against the traffic, because they're not expecting you to come that way. And for instance, when you are driving the wrong direction on Fifth Avenue or something like that, you may notice that the traffic goes south on Fifth Avenue. If you're driving, and this is true to crosstown streets too, if you're driving east, like the even numbered streets go east in New York City, right? They all go east, right? The odd numbered streets go west. Even numbered streets go east. If you're driving west on an even numbered street, you're going against traffic. And the problem is all of the street signs, the traffic lights and everything else, they don't point that direction. So you can't tell that it's a red light, that you have a red light if you're going across the intersection in that direction. So, or you can't tell that there's a stop sign or something like that, because it's not in the place that you would, they don't put it there for people who go in the wrong direction. Okay, so at any rate, if you ride a bicycle, be careful, please. Okay, 550,000 New York that indicated they believe has been effective, calculate 95% confidence in over a true proportion of New Yorkers that believe the program has been effective. The numbers dropped a lot in the last week or so. So at any rate, the idea here is that we randomly sample 1,000 people, but there's 9 million New Yorkers, right? We want to know what all the New Yorkers, or maybe at least if we just said adults, 7 million or 6 million adults, right? We can't sample 6 million adults, so we randomly select maybe a phone survey or something like that. 1,000 people in New York City over 18. And we ask them, do you think it's effective? 550 said yes out of 1,000. But now, how sure are we that that means that the majority of New Yorkers think it's effective? In other words, more than 50% think it's effective. Well, that's why we want to calculate a confidence interval. So our p-cap value the proportion of our sample that say yes is 550 out of 1,000 or 0.55. But now we want to calculate a confidence interval for that proportion. We want to know the confidence interval for the true population proportion. Let's give this a try now. Okay, I don't have a blank sheet, so I'll open one up. Okay. So P cap, right? What we're interested in is P, the true population proportion. We're never going to know that, right? So unless we have a referendum and they get everybody to vote. So P cap is equal to 550 over 1,000 is equal to 0.55. But what's the relationship of this and P cap? Well, it approximates it, but we don't know how well it approximates it. But we can calculate a confidence interval. Okay, in order to do that, we need to take P cap, and we have to add and subtract a margin of error. And that margin of error is going to be equal to, well, you know, when we do these kinds of surveys, we've got very large sample sizes. So if I went to the T table, first of all, you wouldn't have 1,000 on our T table, right, for sample size, right, because it's so big. If I went to the T table, it would be 1.961, you know, be very close to 1.96. So generally, we just use 1.96 for a large sample size like that. It's a little bit of a cheat, but you know, it's not. It's substantially correct. Okay, so 1.96 times the standard error. Okay, now we don't have a conventional kind of distribution, numerical distribution, where we would calculate standard deviation for the sample, but we do have a proportion. And when we have proportions, we say that the standard error is equal to the square root of P times 1 minus P, okay, over N. Okay, so what is that in this case? It's square root of 0.55 times 0.45 over 1,000. Okay, and let's see what that comes out to be. Okay, 0.55 times 0.45 equals this, divided by 1,000 equals this, take the square root of that, is equal to 0.16. Okie doke. And again, I rounded, and I keep telling you not to round until the very end, but I rounded anyway. 1.96 times my standard error, which is equal to 0.016. And again, I'm going to cheat a little bit here, and I'm going to say 2 times that's equal to 0.3032. Okay, 0.55 plus or minus 0.032 is going to be, well, if I add it, that's the easy part, 0.58. 0.582, 58.2%, 0.582. And if I subtract it, it's 51.518, right? So it's between 0.518 and 0.582 is our 95% confidence interval. We're 95% sure the true population proportion lies between these two numbers. Both of those numbers are bigger than 0.50. They're both bigger than 0.50. In other words, 0.50 is not in between them. So we can say with at least 95% confidence that the majority of New Yorkers appears to believe it's working, that this Vision Zero is working. These are fake numbers. I made these numbers up, so I don't know what the real numbers are. It should be interesting to see if they're doing surveys on that. But we're 95% sure it's because outside of the confidence interval. And so let's see how that looked on our answer sheet here. Okay, and 0.58, 0.58, 0.59. We gave you a 100th, so you could go 0.5, anywhere from 0.57 to 0.59 would be right, and so on and so forth there. Okay. Okay. So I think, yeah, 0.59, 0.519. Okay. So Let's see. Okay, so finally, I think we end with analysis of variance. Yeah, good. Okay. This is another thing where I said this a million times, and it's discouraging when you don't get it. Okay, but we have an opportunity now to straighten this out. The null hypothesis for null and alternative hypothesis. This is a great opportunity for me to straighten this out. So going on into the future, you can say with confidence what the null hypothesis for analysis of variance is, and you won't get it wrong. And then somebody will say, "What's wrong with that dolt DeVito? Didn't he teach you how to phrase null and alternative?" I have that. That keeps me up at night when you do this, and I'm afraid that you'll go to the next course and you'll describe it incorrectly. So try and get this right now. I'm going to go over it again. Okay. So first of all. Do random survey university students the political affiliation, find sample averages for the amount paid by Democrats, Republicans, Independent. You wish to compare the means of these three groups to determine if there is difference in the average amount that each population pays for a haircut. Okay, so now we're comparing the means of three groups. Okay, the average of one group to the average price paid by one group, the average price paid by one. So we have three independent samples. Sample Republicans, Democrats, sample independents, three independent samples. We wind up with 3 X bars. And we want to determine whether the actual populations themselves are different. So our null hypothesis is the mean price paid by Democrats is equal to the mean price paid by Republicans is equal to the mean price paid by independents. Everybody got that right. Null hypothesis. Okay, this is important. When we do analysis of variance, we do an analysis which substitutes for a t-test in a way. It's really kind of a t-test. It substitutes for a t-test. A t-test, in order to do a t-test, we would have to compare 2 at a time. Democrats to Republicans, Democrats to Independents, Republicans to Independents. We'd have to do multiple t-tests. The analysis of variance allows us to just do it once. And if we get a large enough statistic, that F statistic for the analysis of variance, if we get a large enough statistic, we can reject the null hypothesis and say that this is not true. I'm rejecting mean for Democrats equals mean for Republicans, mean for independents. However, it's not like doing the t-test 3 times. All you've proven at that time is that at least 2 of the means are different, not 3 of the means. If you write mean for Democrats is not equal to mean for Republicans, is not equal to mean for independents, that implies they're all different, right? So you can't do that. You got to say at least 2 of the means for these groups is different. You really can't set it up the same way as the null hypothesis. So keep that in mind. At least 2 of these groups has a different mean, okay? Or you could say at least 1 of these groups has a mean different than the other 2. That's the same way of saying physically the same thing, but not mu1, mu d is not equal to mu r, it's not equal to mu I. That's not good because we haven't proven that all 3 are different. You might be able to do that when you do the post hoc tests, right? But at this stage, we can't say that. Okay, so we do the analysis of variance, and the analysis of variance comes out to, I didn't give you the data set, so I gave you the output. The analysis of variance comes out to this, right? This is our table for analysis of variance. And we have to fill in what is the F value here. Well, first of all, one thing we see right away, the significance is less than 0.05. So we know we can reject the null hypothesis. Boom, boom, and say at least 2 of these groups is different, right? So we know we can reject the null hypothesis. And how do we get the F score? Well, the F score is the ratio of the mean squares, the sum of squares divided by the degrees of freedom, or the mean squares divided by the sum of squares within the groups divided by the degrees of freedom within the groups, 450. So 2,000 over 450 comes out to 4.4458. That's where that number comes from. Okay, so just as a test of understanding what that table means, can you reject the null hypothesis? Yes, you can. 2 reasons. Now that you know it's 4.458 and you know the degrees of freedom, you can go to the table and look up the critical value of F and so on and so forth. Or you can just look at the significance here, even easier. Okay, so now here's the post hoc test. This is the test that you do after you've demonstrated that the significance is less than 0.05 and you reject the null hypothesis, and at least two of the means are different from one another. Maybe three, but at least two. Okay, so this post hoc test actually, just like the t-test I described, actually individually looks at and compares each one of these groups, Democrats to Republicans, Democrats to Independents, Republicans, and does it for each one of these groups individually, but corrects for the error that might be introduced by doing the test multiple times. So this one I chose Bonferroni, I think, yep, Bonferroni, and gave you the output table. And the key here is we want to look at the significance here, right? So when we compare Democrats and Republicans, the significance is less than 0.05. So they're different. Democrats and Independents is less than 0.05. So the means of those two groups are different. Well, how about Republicans? What do we miss? Democrats, Republicans, Democrats. How about Republicans and Independents? Republicans and Independents, that's not different, right? So if I go down here, Democrats pay a different amount than Republicans. Yeah, I got that. Democrats on average pay a different amount than Independents. Yeah, that's less than 0.05. Republicans pay more for haircuts than Independents. Republicans, Independents. Oh, no, I can't say that. I can't say that it's different. All three groups pay significantly different amounts. That's not true. Republicans and Independents, we couldn't demonstrate a difference. The significance is less than 0.05. So that's it. So now, for the rest of the semester, unless you decide to do a project that involves using the t-test or analysis of variance, we're done with that. Okay, you're done with it. I'm done with it. We're all done with it, unless you decide to do a project, which, if you feel comfortable with it, might be a nice alternative to taking the test. I'm going to talk about that. So no one can say, hang on a second, I want to see what that comment is. No one can say at least one. So one can say at least one of the means is different than the other means, or at least two of the means are different from one another. At least one of the means is different than one of the other means, or at least two of the means are different from one another. It's kind of like saying the same thing. But it could be all of them are different. But all you've proved so far, until you do the post hoc test, the only thing you've proved is the null hypothesis is not true, and that you know that at least two of them are different from one another. But you don't know which ones, or even if it's all of them, or more than two, right? If we had 5 different groups, it could be 3 that are different from one another, 4 that are different from one another, and so on. Okay, so we got that out of the way. We got that out of our hair. Fortunately, the test results for most people did pretty well on the test, or quite well on the test, very well on the test. So I'm hoping that means that that this going forward, that you guys will be able to apply this stuff usefully when you start taking other courses. Okay, so next, what's next? What did I say was next? Next is a quick review of chi-square. And I think right now might be a good time to take a short break. Let's take a 5 or 10 minute break. I'm going to pause the recording, and we'll come back in about 5 or 10 minutes and continue with a review of chi-square. And then I'm going to finish up by introducing correlation and regression.
This conference will now be recorded.
Okay, we're back, and I just downloaded a file that sample data set 2014. I'll put it up on Blackboard later on, but for now, you guys can just kind of look over my shoulder on this. There's a series of variables here: birthday, rank, gender, athlete, height, weight, so on and so forth, smoking status. And you'll notice that some of these are categorical variables, clearly categorical variables. For instance, gender, right? We can see 0s and 1s. Athlete, 0s and 1s also. Most likely it means probably that person took part in, say, collegiate athletics or whatever, or they didn't take part in collegiate athletics. Smoking status. There's several numbers there. 0, 1, and 2 might be something like never smoked, past smoker, current smoker, and so on and so forth. Or the level number of cigarettes they smoke, or something like that. But it's categorical variable as well. Okay, it's described as a level. Okay, so when we want to evaluate whether there's a relationship between categorical variables, for instance, gender and whether or not they take part in college athletics, right? That gender is a male and female. Athletic is yes or no. They take part in it or they don't take part in it. I'm going to fill in the variables, the value labels for those variables. Not in here, but I'm going to make it up. So I'm going to say 0 is female, and I'm going to say 1 is male. And for athletes, I'm going to say, I hope it was, let's see, value 0 is athlete. Did I spell that right? I don't care if I spell it right, it doesn't really matter. Or 1 not. Okay. So I'm going to go back to the data view, and you can see it kind of filled in there and so on. So now I want to determine whether there is a relationship between a gender and whether or not you're likely to take part in college athletics. Okay, so my null hypothesis is there's no association between what gender you are and whether or not you're likely to take part in college athletics. My alternative hypothesis would be that there is an association, that perhaps males or females are more likely to take part in college athletics. So I have something like, how many people are in this study? A random sample from many colleges of 535 students. And I want to see if this is a sample, remember, not the entire population of all students, right? So I want to see if there is an association there. So since they're both categorical variables, I can't compare means. They're not numerical variables. I can't do analysis of variance, can't do t-test. So I need another test. So that test is going to be chi-square for us, chi-square and odds ratio. Relative risk also, but that's not quite used quite as often, similar to odds ratio. So I'm going to go up here to analyze. I'm going to say the first thing I want to do is to organize this into a table, right? So I got gender is my exposure. In other words, gender, I want to know whether you're more or less likely to be involved in athletics by gender. So gender is my exposure. I'm going to go organize this into a 2x2 table. So let's see, I'm going to go to Descriptive Statistics to crosstabs. Okay, it's hidden there in crosstabs. And I'm going to put these back so you can see me put them in. So in the rows, I'm going to put in gender. So all of my, so the rows are going to represent female and male, right, top and bottom row. And athlete, whether or not you're an athlete, is going to be represented by the columns. First column, you're an athlete. Second column, you're not an athlete. And I'm going to click OK. So first I'm going to go here. And I'm just going to make sure that all I'm calculating here is my observed values. And this is going to organize this into my observed values. Okay, where am I? Here are my observed values down here. I'm going to shorten this so you can get it further up on the page. Here are my observed values. There are 496 subjects, people in these that were selected, randomly selected. About 98% of them answered the questions that didn't have missing data. And this is what we found. We found that 426 of these people, 103, there were 204 females, and there were 222 males. Of the females, 103 of them were athletes. Of the males, 143 out of 222 are athletes. Okay, so now I want to test my assumption that there is no relationship between gender and whether or not you're a college athlete or not. So first thing I'm going to do is I'm going to take a look at what my expected values would have been if there was no relationship between these two. So unfortunately, SPSS does this without creating a new table, but actually just displays the data in the same table. So I'm going to go into cells. I'm going to ask it to calculate my expected values. So if there's no association between gender and whether or not you were a college athlete, you would expect that out of 204 females, that 118, roughly 118 of them would be athletes. In fact, only 103. So they're underrepresented in my observed values. And the males, in the meantime, we would have expected out of 222 if they competed in athletics at the same rate for both males and females. Out of 222, we would have expected 128 males to be athletes. In fact, 143 were observed. So they're overrepresented. So it looks like more males are taking part in athletics in this population than females are. Okay, so it seems like there might be an association, but this could be just due to chance. So in order to determine if it's just due to chance, we have a few tools at our disposal. One tool is to calculate the relative risk for being an athlete. It's kind of an odd way to phrase it, but I'm going to go up to Analyze. I'm going to go to Descriptive Statistics crosstabs, and this time I'm going to go into the Statistics box. And I'm going to tell SPSS to calculate the risk, whoops, that's not what I want. I want to go into the cells. I'm going to ask SPS to give me the percentages by rows that are represented in this table. I'll click OK. And let's see what my table looks like now. Oh, you know, the other thing I'm going to do is get rid of the expected values because they just make it harder to read. We don't need them anymore. Oops. Okay, so let's see what we have now. So now we can see that out of these 204 females, we have 103 that are athletes. So 50.5% of the females are athletes. How about the males? Well, 222, 143 are athletes. That's 64.4%. So 103 over 204 is 50%, and 143 over 222 is 64%. So the rate at which females are athletes is 50%. The rate at which males are athletes is 64%. So the relative rate, better, maybe in this case, a better term than relative risk. The relative rate is 50% over 64%. And what does that come out to? Well, I'm going to do this just now because it'll come up later on. So not a number. It's not a number. I haven't typed anything in yet. 50.4% divided by 64.4%. My relative rate is 78%, 78.78. So my relative rate tells me that females are 78% as likely to be athletes, college athletes, as males are. In other words, females are less likely to be, or lower risk of being an athlete than males are in this particular population. Okay, so let's keep that in mind. We'll remember that. And how was that calculated? That was calculated by the percentages, which are really 103 over 204 divided by 143 over 220. We're also later on going to calculate an odds ratio, which is 103 over 101 divided by 143 over 79. Similar to our risk ratio or rate ratio, but we're going to use just the number of people that are athletes over the number of people that are not athletes in the female group, and same thing in the male group, and just take that ratio instead. Okay, that's also going to show us that the odds of being an athlete, if you're a female in this population, are probably less than they are if you're a male, because it'll be a proportion that's less than 1. If females, 50% of females or 50% of males were both athletes, 50% over 50% would be equal to 1. So the relative risk, if there's no difference or relative rate, is 1. If there's no difference in the odds, the odds ratio is equal to 1 as well. So we're interested in whether or not that odds ratio, relative risk are equal to 1 or not, to see if there's a difference between males and females in terms of athletics. So now we also can calculate a chi-square value. And the chi-square value compares the observed values to the expected values. And we'll talk about that after I finish doing the calculation. We can move this data over to Excel. So I'm going to go up here. I'm going to say Analyze. I'm going to say Descriptive Statistics and cross tabs. And this time, I'm going to go into Statistics. I'm going to ask SPSS to calculate a chi-square value, and I'm going to ask it to calculate also risk for me as well. And again, keep in mind now, the chi-square value. How did we calculate the chi-square value last class? We took the observed value in each cell, observed value. We took the observed value, subtracted the expected value, and squared it, and divided it by the expected value. And then we went to the next cell and did that 4 times. We went to each of the 4 cells, comparing the observed and the expected values. We added those numbers together to get the total chi-square value, and then compared that to a table of chi-square probabilities to get a critical value for chi-square. For a 2x2 table, which is 1 degree of freedom, because degrees of freedom are rows, the number of rows minus 1 times the number of columns minus 1. So 2 minus 1 is 1, 2 minus 1 is 1, 1 times 1 is 1. So 1 degree of freedom. And the chi-square, critical value chi-square was 3.84. So in order to reject the null hypothesis and say that there's a real difference between the observed values and expected values, is that chi-square value has to exceed 3.84, the critical value of chi-square. So I'm going to go ahead and complete this calculation. Say OK. OK, and what did I get for my chi-square? My chi-square comes out 8.447. Well, that's interesting, right? Because it's greater than 3.84. So that suggests I can reject my null hypothesis for 1 degree of freedom. And in fact, SPSS actually gives me a calculated p-value or probability that we would get that big a chi-square value if the null hypothesis were true, that there's no association between gender and whether or not you participate in athletics, right? So we can reject the null hypothesis and accept the alternative hypothesis. Well, how about our risk ratio? Remember when we talked about relative risk or relative rate and odds ratio? Well, this first number is the odds ratio. The odds for gender taking part in male versus female taking part in athletics, and it comes out to be 0.563. But what do we need it to be different than? We need it to be different than 1, which would be the ratio if there were no difference between males and females. So we can't just take that, we have to look at the confidence interval to make sure that it doesn't include 1. So our null hypothesis here is that the odds ratio is equal to 1 is our null hypothesis. In other words, there's no difference in odds for males or females, or the odds ratio is not equal to 1, right? So can we reject the null hypothesis that it's equal to 1? Well, let's take a look at it. Our 95% confidence interval is 0.38 to 0.83. So it doesn't include 1. So we can say with 95% certainty that it's not 1. Since it's not 1, we can reject the null hypothesis that the odds ratio is equal to 1 and accept the alternative hypothesis that it's not equal to 1. In other words, the odds of females taking part in sports are like 56% of the odds. 56% is likely to have odds of females taking part in sports as males. And in fact, here's our relative risk, or risk ratio is the next line. We calculated that from our 2 percentages, 50% and 64%, and it comes out to 0.784. And similarly, that excludes 1 in the confidence interval. So more evidence we can reject the null hypothesis. Okay, so are you guys comfortable with that? Does that make sense to you? This is a quick review of what we did during our last session. It would probably be better if you went back and watched the video from the last session. You actually saw us work through these problems using Excel step by step. But you should give that a look. Now, the last exam, exam 3. Exam 3 will include chi-square, correlation, and regression. Okay, now you have an option here. And the option is, instead of that, you can do a modest project. And what the modest project consists of, I will put up several sets of data, right? Most of it is from a annual health survey, community health survey that New York City does. They survey, I think it's phone survey, survey 8,000 people in the city of New York. They go through an extensive questionnaire with them about their health, about whether they smoke or not, what they drink, what their diet is like, how much exercise they get, if they've sought mental health treatment, if they are taking drugs, so on and so forth. So they ask them a number of questions, and they accumulate that data, and we can download that and examine that data. Okay, so I also have some data that you can work with. That's statistics on whether people are likely to get an influenza vaccine if they have insurance or if they don't have insurance, by gender, by income level, by ethnicity, and so on and so forth. So as an option, instead of taking the exam, you can, and I'll post in the next day or so, I will post guidelines for this. You can choose to take one of those data sets, choose any couple of variables that you find interesting, and analyze them. Try and apply the correct statistical test. In other words, if you're looking at males and females and you're looking for whether or not they're more likely to have diabetes or not, those are two categorical variables. You would use chi-square or odds ratio and so on. If you want to compare BMIs for males and females, that's numerical variable for two groups, so you would use a t-test. If you were looking for the amount of sugary drinks people drink per month, a numerical variable, and ethnicity, that might be numerous means for several, it's more than two categories. Ethnicity means more than two groups. That might be analysis of variance, right? So you would choose the correct test. You would put together an introduction stating what you're examining and what you wish to prove. Then give us some descriptive statistics about the population. In other words, if you're comparing gender and diabetes, what percentage of the population is male and female? What percentage has diabetes? And so on. And maybe a couple of graphics to demonstrate that, a pie chart or a bar chart. And then tell us what your null hypothesis is, and give us your statistical test. Tell us what statistical test you use. Give us your results. Put your results in there, and then give us some discussion, some discussion and conclusions about your results. And in addition to that, just one or two references to somewhere in the literature that you can find something that gives you some insight into someone else that has examined that as well. So, like, in other words, if you're interested in diabetes rate and gender, I'm sure you can find a reference or two that you could just drop in there that you could read and mention in your project. So it can be like anywhere from 4 to 7 pages, and it can be. I'm going to give you a couple of different formats that you can use. One of the formats that you can use is to put it together as kind of a PowerPoint or as a poster presentation. Okay, so that'll even kind of like help you organize it, help you do the graphics on the charts and so on and so forth. So you don't have to make that decision now. I will post by Wednesday. I will post the data sets and the instructions, and you can choose. When I post it, our last class, believe it or not, we're getting real close to that. We have a class on Wednesday. We have a class on Monday, and our presumably last class would be the following Wednesday. Now, normally that's the day I would give the third test, or in a brick and mortar class, I often have the students come in. They don't have a choice. They have to do a project, not an exam. And they come in and do a 5-minute presentation on their project, right? Which gives them a little bit of exercise in talking to a room full of colleagues and describing what they've done and verbalizing what they've learned as well. So unfortunately, we're not in that situation here. So the last class will be either you can submit the exam or you can take the exam or do the presentation. Okay, the exam again will be online. I'm not going to be as liberal this time with the number well, maybe I'm not going to be as liberal with the number of attempts this time. I think that everybody got a chance to really do well on the first 2 exams, and that's very nice, but I want to test you on this last one. I'm not going to make it, I'm going to make it relatively easy, not challenging, but it is 3 new topics for you. Chi-square, correlation, and regression. So it is 3 new topics for you. But the questions on it are not going to be that challenging. But I'm trying to make my mind up exactly how to do this, not jam you up so like you're completely ill prepared for it. I may give you 1 chance at it, but not put a time limit on it. So like in other words, then you can stop, go away, go back over stuff for a little while, go back and continue, right? So even if you only have 1 shot at it, you don't have to submit it until you're happy with what you're submitting. Okay, I think that might be a good approach, because that way you're not going to be like a deer caught in the headlights, right? You're going to be able to see what it is and react to it. Okay, so I think that's a nice compromise. Okay, so I think that's where we are with that. So I'm going to leave this on this chi-square, and I think between now and then we'll have a review where I'll go over the chi-square again. But again, if you haven't seen it, if you haven't actually looked at the video from the last class before the exam, when we did chi-square step by step using Excel, then you should go back there and take a look at that. Okay, so I want to move on now to get started in correlation. We're going to finish up today with correlation, and on Wednesday, we're going to move over to regression. That'll give us Monday to really kind of like, like rehash all this stuff, finish up with a couple of advanced topics in regression. In other words, like multiple regression, logistic regression, and so on, which will not be on the exam, but it may be something that may be important to you, be exposed to, so you know what it is in the future. Okay, so we're going to stick, in the exam, we're going to stick to simple linear regression. But on Monday, I want to at least spend some time on multiple regression and logistic regression. Okay, so let's move on to correlation. Okay, let's see what we have here. Gonna want to have Blackboard open while I'm doing this. And I wonder if I already do. No, apparently not. Can you still see that? Is that still up back there? That's still working?
Yeah,
okay,
yeah.
good. Okay, good. Okay, so first thing I want to bring up where this is concerned, I'm going to open up an Excel file called pizza versus Subway fare. Okay, and the reason why I open that up is because I don't know how many of you have heard this old song, but a lot of people think that there is a mysterious relationship between the price of a slice of pizza and the Subway fare. So when I first started taking the subway many years ago, the fare wasn't 1960, it was a little later than that. But the price of the subway was 15 cents. That little little tiny round token, about the size of a dime in it with a little slit in it. And you bought that 15 cents, you got on the subway and so on and so forth. And I'll be posting the recording within 24 hours. Okay, so the subway token was 15 cents. And if I went to the corner and bought a slice of pizza, it was 15 cents also. Okay, well, fast forward to now, and whoops, wait, 2019. Hang on a second. Okay, and the subway fare is what, $2.75 now, right? How much does a slice of pizza cost? Not $3, right? We're still under $3, right? I think it's $2.75. It's about $2.75. I'm not talking about that weird dollar pizza stuff. God only knows where that cheese comes from. I don't know what that stuff is, right? But I mean a real pizza store where you go in and buy a pizza for 20, full pizza for $20 or $25. A slice of pizza there is usually around $2.75 or $3, right? Okay, so maybe it's $3 now. I'm gonna put $3. But look, it looks like it's the same thing. It looks like there's an association between those two. In fact, what we're seeing an example here is a correlation. There's an association between the cost of the subway and the cost of a slice of pizza. Now, when I say correlation, when I say there's a correlation or association like that between these two variables, I'm not saying, when I use the term correlation, I'm not saying that there's a causation, that the subway fare causes the pizza price to go up or vice versa. I'm saying that they're just associated. It may be just that there's some weird coincidence between the cost of the materials making a pizza, or the cost of real estate, or rent, or a store and pizzeria, something like New York, and these in the subway fare. Maybe that's the association, but maybe there's some background association there that would suggest to me that there is a correlation between the price of a slice of pizza and a subway fare. Okay, so now it's interesting. I want to be able to demonstrate whether that association is really true, if that's a strong association or a weak association, and whether it's due to chance and not due to an actual association between the two. Okay, so how am I going to do that? Well, first of all, what kind of variables are the price of a pizza and price of a subway? They're both numerical variables. So up until now, what kind of variables were we working with? Well, when we were working with a categorical and a numerical variable, we did a t-test. When we were working with a categorical variable that had more than two values and a numerical variable, we did analysis of variance, right? When we're working with two categorical variables, we did chi-square and odds ratio. Now we have a new kind of situation. We have two numerical variables, and we want to see if there's an association between the two of them. So what's my null hypothesis here? My null hypothesis is that there's no association between the price of a slice of pizza and the subway fare. Okay, well, what's a good way for me to kind of look at this, besides kind of just looking at this jumble of numbers, that'll help me understand this? And what I'm going to do is I'm going to open this up in SPSS. I have the same data set. I'm going to open up in SPSS so I can examine them. Okay. Keeps warning me about my license. It's just going to make it to the end of this summer session. Okay, so here we go. I'm going to add in the last one I just added, 2019, $3 for a slice of pizza, and $2.75. Oops, I made a mistake there. 25, it should be $3. Okay, I added in that last piece of data that I was talking about. Okay, so now, I want to see if there's an association here. Sometimes it's easier to see something graphically than it is to just see a jumble of numbers. So let me graph these two numbers. I'm going to graph it on an XY coordinate. I'm going to call the pizza the X coordinate and the Subway the Y coordinate. So for 1960, I have a point on my graph that X is 0.15 and Y is 0.15. And then X is, for 1973, X is 0.35 and Y is 0.35 and so on and so forth. Okay, so I'm going to go up here to graphs and I'm going to go legacy dialogues. I'm going to go to scatter plot. I'm going to call that a scatter dot. And each one of those dots represents the association between the price of pizza and the Subway fare. So in the x-axis, I'm going to put the cost of a slice of pizza. And in the y-axis, doesn't matter which one I'm going to put in there because it's not cause. I'm not saying that one causes the other. The y-axis, I'm going to put the Subway fare. I'm not going to bother with titles and stuff like that. So I'm just going to say, okay, see what I wind up with. Okay, and here's our graph. Well, that's a pretty dramatic graph, right? What does that graph tell you? Whoops, made it go away. Right, so what do these dots represent? Well, this dot represents when pizza cost $1.35, it looks $1.30 it looks like, and the Subway fare was, I don't know, $1.40 or something like that. So actually, I guess it's $1.35, $1.25. So that's probably 1995, that dot represents. So this is the x-axis and this is the y-axis. So each dot represents 1 year, what the slice of pizza was, what the cost of a Subway fare was. So what we see here is that it's very dramatic that as the cost of a slice of pizza goes up, the cost of the Subway goes up also. This demonstrates to us that this has a pretty strong correlation, right? What kind of correlation is this? Is it one where they both go up at the same time, where one goes up and the other goes down? They're both going up at the same time. The pizza price goes up, the Subway fare goes up. That's called a positive correlation. Okay, not all correlations look this clean. Many of them, look how close these things are to forming almost a straight line. Right? We could almost draw a straight line here if we wanted to. Okay, in fact, SPSS just drew a straight line for me that approximates the line that is the best fit for all of these different values, where half of them are above, half of them are below. Only a couple of them wind up really exactly on. In fact, none of them really wind up exactly on the line. But this gives us a rough idea of what the slope of this line is, how fast they're going up relative to one another. Okay, and that where this whole thing crosses the y-axis. What happens when the cost of a slice of pizza is 0, which never happens, right? It was never 0. So we can get a rough idea of what this relationship looks like. Is the price of pizza causing the Subway fare to go up? No, we're not concerned about causality. We're only concerned in terms of being able to demonstrate that this is a real association or not a real association, a real correlation or not a real correlation. Okay, not necessarily causal, but just that this is not just simply due to chance on the numbers that I took. And that can happen. You get a lot of odd things happen by chance. I'll show you that in a second. Okay, so let me give you another example of an association that is a positive correlation, but is not causative. Okay, let's think about this. When there's a fire, right? Is there an association between or correlation between the number of firemen that respond to the fire and the amount of damage at the fire? Yeah, it makes sense, right? It's a big fire, you could send a lot of firemen. Small fire, they only spend a few firemen, right? So are the firemen causing the damage? Yeah, sometimes they cause a little bit of damage, but not in a big way, right? So, but largely it's just because there's this other hidden association. Big fire, a lot of firemen have to respond to it, but there is a correlation. Correlation is real. As the fire gets bigger, more firemen respond, and it means that it almost always means that there's more damage. Right? So there is a correlation that's real there. Maybe not a direct causative association, but there is a correlation. That is a correlation. So I need to calculate a statistic that tells me how strong is this correlation. I need to invent a statistic that I can use that we can universally understand describes how strong this association is. Is it a weak association? Is it a strong association? That's called Pearson's correlation, or Pearson's R. I'm going to go to Analyze, and I'm going to go to Correlate, and I'm going to go to Bivariate. Why Bivariate? I have two variables. I have the cost of pizza, and I have the subway fare. Okay, so I'm going to move in my variables, the cost of a slice of pizza and the subway fare, into my variables. Okay, I have some options, but Pearson's correlation is primarily what I'm interested in here. And I'm going to click OK. Okay, next week I'll go over a little bit on how it's calculated. It's not something you really absolutely need to know, but you might want to be exposed to it at least. Okay, so here's Pearson's correlation. Okay, so if I look at this, it tells me when I compare the cost of a slice of pizza and the cost of a slice of pizza, I'm comparing the same thing, so the correlation is 1. 1 is a perfect correlation. Okay, well, how about cost of a slice of pizza compared to the subway fare? That correlation is 0.995. It's pretty close to almost perfect correlation, right? Hence the pizza subway coincidenza, as we like to call it, right? That there it seems almost magical, right? That there's this kind of strong association, right? So that's a very strong association. That value is called Pearson's correlation, or when you talk about it for the population, it's rho, the Greek letter rho. When you talk about it for a sample, it's R, right? Lowercase r. Pearson's R, or Pearson's correlation. Okay, and that's 0.995. Any number that's close to 1 is a very strong correlation. Any number that's close to 0 is a very weak or no correlation. 0 represents no correlation no association correlation between your two numerical variables. What do you think a correlation of -1 might mean? It exists, right? Okay. It exists. -1 exists, right? What do you think the negative implies? Negative correlation. Bingo. And a negative correlation means as one goes up, the other one goes down. So that line would be sloping downwards rather than upwards. So a negative correlation. So anything 0 is no correlation. Anything that gets closer and closer to -1 or +1 increases the level of correlation, the level of association between those two numerical variables. So a correlation of, and if I look here, you'll notice that the significance is 0.000, right? In other words, our null hypothesis here is rho is equal to the correlation is equal to 0, no correlation. Our alternative hypothesis is rho is not equal to 0, right? So what does the significance of 0.000 tell you? That means you can reject your null hypothesis at 95% and accept your alternative hypothesis, that rho is not equal to 0. There is a real correlation. So this tells us there's a real correlation, and the number 0.995 tells us how strong that correlation is. So let's assume that that in each of the examples I give you, that the significance is less than 0.05. So they're all significant. What if I told you that the R value, Pearson's correlation value, is 0.5 plus 0.5? What would that tell you? A moderate association between the two, but it's real because the significance is less than 0.05, right? It's not an active. How about 0.1? That's a very weak positive association between the two of them. If the significance is below 0.05, it's a real correlation, but it's a weak correlation. In other words, if we looked at those dots, they would be scattered quite a bit, but you should still be able to see kind of they go up. How about -0.8? -0.8. It's a negative correlation, but a weak one or a strong one? It's pretty close to 1, right? So it's a strong negative correlation, right? So that's the idea. You could predict how strong the association is from the Pearson's R value. Right? And the closer it gets to 1 or -1, the stronger the association, the closer those sample points are going to be to a straight line. And the weaker the association, closer to 0 it is, the weaker the association, and the less they're going to be close to a straight line when you plot them using a scatter plot. Okay, so let's take another look at this. Okay, just to show you a couple of examples here. I just want to emphasize the fact that these are not necessary. That when I say that you come across many things where there are these strange associations, but they don't make a lot of sense from the point of view of what's even though there may be an association that seems real, there's no causality. It's just random, just occurs randomly. Okay, the more people eat cheese, the more people that are killed by their bed sheets, right? There's a study that this fellow does. This guy collects, and I gave you the link on Blackboard if you're interested in it. Let's see. Here we go. Miss America correlates with murders by steam, hot bakers, and hot objects. Right? And if you look at this graph here. This is a graph for all these different years of the age of Miss America and the number of murders by steam, hot vapors, and hot objects. Right? He just randomly puts these together. Look at the correlation. Correlation is 0.87, right? A strong positive correlation. The per capita consumption of cheese correlates with the number of people who die by getting tangled in their bed sheets. And there's the proof right there. Right? Now, are any of these causative or are these just coincidence, right? Okay, good. So you can go through, he's got a ton of them over here. Okay, U.S. spending on science, space, and technologies correlates with suicides by hanging, strangulation, and suffocation. And you can go through some of these, they're pretty interesting, but this guy has, gone through these things to the per capita consumption of mozzarella cheese correlates with civil engineering doctorates awarded in the United States. What's the level of, look at this correlation. It's almost a perfect correlation, right? And these are real numbers. According to him, I haven't checked them, but according to him, they're real numbers. Again, who knows, maybe there's some underlying reason why this is true. It's got something to do with the economy or something like that. But he's made it his life's work to go and track down all these different correlations that really, when you really get down to it, are really pretty meaningless. There's a word for that. It's called spurious. These are spurious correlations. They're really meaningless. They don't really make, they're not useful or meaningful numbers or correlations that would be useful. Worldwide non-commercial space launches and sociology doctorates. We're getting a lot of launches here. So for those of you that are looking for sociology doctorate, in the next couple of years, you're in luck because a lot of space activity, so therefore there must be they're going to be awarding a lot of doctorates, I guess. And again, it's not quite as strong, but pretty strong correlation as well. Okay, so I just wanted to show you that to give you an example that just when you say correlation, when things correlate with one another, you're saying that there's an association. As one goes up, the other seems to go up as well, but it doesn't necessarily have to be causative. One doesn't have to be causing the other to go up. When we get into regression, we want to take these correlations that are real, and we want to focus on the ones where there is really an association. So, for instance, we might want to show that there's an association between BMI and blood sugar levels, or insulin sensitivity. Both of those are numbers, right? You test somebody's blood, you can calculate BMI, test their blood for insulin sensitivity. Higher insulin sensitivity means you're more likely to develop diabetes, I guess, right? And so on and so forth. So you'll see if there's an association, there really probably is causative. There may be something about high BMI that causes indirectly or directly causes higher insulin sensitivity. So that's something you want to understand. Why is that important to you? Because then you know that for this physical thing that you can measure, you might be concerned that there might be this correlation, this association with this disease. And you might want to say, well, anybody with a BMI above a certain level, the likelihood of insulin sensitivity is so high that maybe I want to test everybody that's above that BMI. Age, for instance, you might want to test. There might be a correlation between male age and PSA test, PSA number, right? Prostate-specific antigen, right? So you might want to say, well, gee, there's an association between age and this number, so maybe I can use age to focus on who I should be giving PSA tests to, and so on. In other words,
how do they base their scientific articles on, like all the correlation? They start doing that, and then they'll say, like, okay, like due to these results, this is what I found out.
Right.
Men have, some common diseases more than women.
Yeah, of course. Yeah, it's all based on all these kinds of studies.
Mm-hmm.
So, for instance, if you might take a couple of factors, BMI, gender, so on and so forth, and you might combine those and try and say to yourself, well, how does this affect the probability of that person being diabetic, right? And you might say, well, if I combine all these three different factors, that's called multiple regression. Combine more than one factor or look for a correlation, more than one factor, right? Age, BMI, gender, so on and so forth. Let me combine all of those things, see if there's a correlation with being diabetic, if it affects the probability of being diabetic. And you may say to yourself, well, once that probability gets over a certain level, I want to screen those people for diabetes. I want to do a, what is the test they do for diabetes? It's more rigorous than just a, it's like a challenge test, where I think you drink some sugary stuff and they test your blood over a period of time or something like that. It's a more aggressive test than just a fasting blood sugar.
Yeah.
Right. So you may say to yourself, well, these factors pile up, given the correlation they have with diabetes, maybe when they get to this level, when they get to this number, then that's the time that we want to send a patient for this test. Okay. So there's a trade-off between. Remember we were talking about diagnostic tests. Same thing with diagnostic tests. There was a couple of graphs that we played around with in some of the in the PowerPoints, where we talked about if the test level was set at everyone over 100, we're saying it's positive. Everyone under 100 is negative, right? Well, if we move that level down to 80, we're going to get more positives and fewer negatives, right? So one of the judgments that you make when you decide on a diagnostic test, how to employ a diagnostic test, is where you're going to set that level. And you're going to set that level at a level where you're not going to miss too many people that have the disease, but then you're not going to have too many people that don't have the disease above that level, right? You're going to look for a happy median. But moving that level up and down is going to affect your predictive value, the positive predictive value. But there are charts that we had in the PowerPoints that kind of demonstrate that. Okay, so getting back to this, let's do another example of this. Okay, let me just see, I got a couple of questions there. Never correlation is relationship. Okay, I'm going to give you a couple of examples right now. Okay, let me get back to. Okay, and we have this document on Blackboard, correlation and simple linear regression. Okay, and I go through an example that compares patients, a random sample of 10 people. Their age has their ages and their blood sugars, and you want to look for whether or not there's an association between age and fasting blood sugar level. Okay, and again, this is kind of bogus data, but this goes through step by step how to do this in SPSS. Okay, and I'm gonna maybe I'll start with that one. We'll take a look at that, and I'll do a few examples. Okay, and here's aging versus blood sugar level. That's this example. Okay, so here we have 10 subjects. We recorded their age and their blood sugar level, and we want to know if there's an association between age and fasting blood sugar level. Fasting blood sugar level, common screening technique for diabetes. Okay, so I'm going to see if there's an association between these two. The first thing I can look for is to see if I notice one graphically. I'm going to go up to Graphs, Legacy Dialogues. You can use Chart Builder and some of these others if you want to play with it. This is just simplest and fastest. I'm going to go to Scatter Dot and Simple Scatter Dot. And I'm going to tell it I want to see if there's an association between age and blood sugar level. Now, up until now, I haven't been worried about whether one causes the other or if it's causative. Blood sugar level, I don't think causes you to get old. Right? I think you do that on your own. But aging may affect your blood sugar level. So I'm thinking that aging is the independent variable or causative variable, and blood sugar is the result or the dependent variable, right? So I'm just going to get now into the habit of going a little bit further and thinking about causality to see if maybe there's something there. So I'm going to put the independent variable or causative variable, age, into the x-axis. I'm going to put the dependent variable or the output or the variable, dependent variable, into the y-axis. Okay, and then I'm going to click OK. And it's going to take each one of these and plot them on an XY plot with the person's age being the x coordinate and their blood sugar level being the y coordinate. See how this one looks. Okay, so let's take a look at that. So if you were looking at this, would you say to me that you see a correlation between blood sugar and age? What do you think? It looks like, yeah, but there's a dot up here. There's a dot here, dot here, dot there, dot there. It looks like a positive correlation, right? Right. It looks like as age goes up, blood sugar levels go up as well. But it's not a very strong association, is it? Not as strong as the one with the pizza and the Subway fare that we saw before, which almost everything fell on a straight line. If you double click on the a chart in SPSS, it brings up a chart editor. And one of the things you can do is ask it to create a best fit line for you. This one over here says add fit line at total. I'm going to click on that. And it's going to add a best fit line for me. Now this line represents the straight line that best estimates the relationship between age and blood sugar. Notice that a lot of the dots are above the line, a lot of them are below the line. The way this line is created, it kind of like your first glance would say, maybe it's just balancing this, the difference between this height in the line, and this height in the line, and this, and it's balancing the differences. It does more than that. It takes the square of those and balances this to the squares of the dots below it. So it creates a line which is an estimate of the best value for the averaging all of these different dots. Right? So this gives us an impression overall that if we had many, many more people in this sample, that they would kind of fall close to this line or around this line somewhere. So we can see that there seems to be a weak association, positive association or positive correlation between age and blood sugar. Now, how are we going to quantify that? How are we going to check to see if that is due to chance or if that is real, and how strong is it? Well, okay, due to chance, we have to do an analysis. We have to test our hypothesis. Our hypothesis is there's no association or correlation between age and blood sugar. Our alternative hypothesis is there is an association or correlation between age and blood sugar. And in order to determine if I can reject my null hypothesis and accept my alternative hypothesis, I have to do another test. I have to go here to analyze. I have to go here to correlate, bivariate, two variables. And I'm going to put these two variables in here. Notice I can put them in any order I want because it doesn't care which one causes the other. I just laid it out that way because it's convenient for me to have the causative variable in the x-axis and the result variable in the y-axis. But we don't need that for correlation. Pearson's correlation is checked off, two-tailed significant test, and then I'm going to click OK. And we get a calculation, and output tables comes up. And what does our output table tell us? Our output table tells us, number one, that there is a correlation between these two, and the correlation is 0.82. It's pretty good correlation. It's not as good as the other one that we had. And is it positive or negative? Is there a negative sign in front of that? No, it's a positive correlation. As age goes up, blood sugar goes up, right? Makes sense, right? Now, can I reject my null hypothesis? Well, it's different than zero, but before I can reject my null hypothesis, I have to be 95% certain that I couldn't have gotten that result when the null hypothesis was true. What's the probability I would have gotten that result given this small a sample if the null hypothesis were true? It's 0.004. It's 0.4%. Since that's less than a 5% chance of getting this result, if the null hypothesis is true, I can then say that the null hypothesis is not true, reject the null hypothesis, and accept the alternative hypothesis that there is an association or correlation between these two. Okay? Let me open another one.
How does a negative correlation look?
I'm gonna see if I can't come up with one. Okay, so here we go. Here is 50 states in the District of Columbia, so we should have 51 lines here. 50 states, District of Columbia, we have the amount of violent crime, that is violent crimes per 100,000, I guess. The murder rate, 7.4 per whatever it is, 100,000 or 10,000. Poverty rate, this is a percentage of the population that's below the poverty line. High school, percentage that graduated high school, percentage that have some college, percentage of single parent households, unemployment rate, and the a rating of how metropolitan the area is. In other words, is it metropolitan or is it rural? And it's a numerical rating. So these are all numerical variables. So let's see, you think maybe that there is an association between the murder rate and the poverty rate. How's that sound? Might be, right? So what's our null hypothesis? Null hypothesis is that there's a correlation between the rate of poverty and the murder rate in a community. So I'm going to go up here to analyze. I'm going to go to correlate bivariate. I'm going to move in the murder rate, and I'm going to move in the poverty rate. Okay, but before that, I'm going to go back up here. I'm going to go to graphs, legacy dialogues, scatter dot, and I'm going to take a look at a simple scatter dot for these two variables, for the murder rate, poverty rate, and the murder rate. And I'm going to say, okay, let's see what our plot looks like. Okay, kind of hard to see, right? Well, geez, they're all trapped down here. Kind of really hard to see. They're all down here. Well, what's this one up here? That's an outlier. What is that doing there? The murder rate is 40. There's no place else that's even close to that. What is that? Where do you think that might be? Actually, you can. There's a way for you to tell. I just want to show you that there is indeed a way for you to tell. If I click on that, come on. I should be able to tell. Should be able to get it to tell me the number. Okay, where is it? Go to case. There's the case right there. You can go to case. That's a right click. Click on the dot. Go to case. District of Columbia. It had an enormous murder rate that year, right? For whatever reason. You know, I think that number one, it's not really a state. It's much smaller than most states. It's a special case. There might have been some reason why it had a very high murder rate. I'm going to remove this from my database. I'm going to clear this out because I want to work only with the 50 states rather than District of Columbia. Now I'm going to take a look at my graph again. Legacy dialog, scatter dot, scatter. Okay, let me give this a try again. See how it looks now. Oh, I didn't get rid of it. It's still there. Why is it still there? It's not still there. I don't see it. Right. Maybe, let's see, well, maybe I looked at an old graph. Okay. Ah, here we go. Oh yeah, I looked at the old one. I didn't scroll down far enough. Okay, now we can see a little bit better that it looks like there's an association, a positive association. How strong is it? How strong a positive association? Let me put in a fit line here, see what we can see. Well, not much of a slope there, right? And look, it does go up, but look at all these things that, you know, scattered lower, higher, lower, they're all over the place. I'm not too confident about this one. So let's do our Pearson's correlation. Let's quantify this now. Go to analyze, correlate, bivariate, and let's see, murder rate and poverty rate. And let's see what we wind up with our Pearson's correlation. Pearson's correlation says that the correlation is 0.427. It's a weak association, right? It's not a great association, but it is an association, not zero. Can we reject our null hypothesis that the correlation is not zero? In other words, there's no association. Well, we got to go here to significance. We can, because it's less than 0.05. It's kind of hard to see, I know, but it's less than 0.05. Since it's less than 0.05, we can reject the null hypothesis that there's no association or correlation between poverty and the murder rate, and accept our alternative that there is an association. Is it causative? We don't really know yet, do we? I mean, it could be a lot of reasons. Okay. So let me see if I can't find one that is a negative correlation. And I might even be able to find one in this same data set. How about, let's see, how about the unemployment rate and the poverty rate? As the unemployment rate goes up, the poverty rate probably goes up. So poverty rate goes up. How about high school graduation and poverty rate? How's that? Let's give that a try. Let's say correlate, bivariate. I'll be poverty rate in there, and I'll move high school graduation, and I'll click OK. So as the rate of high school graduate, as I should have done the graph first. Okay, let's take a look at the graph first. High school graduation rate for each of the states and the poverty rate for each of the states. Let's compare them and take a look at that. What's happening there? Right? That one looks like it's a negative association. Okay, and indeed, when I put in a best fit line, it slopes downwards. So as the high school graduation rate goes up, the poverty rate goes down. Let me switch those axes around. Graphs, scatter dot. Okay, I'm gonna switch these around. Okay, there you go. As the high school graduation rate goes up, the poverty rate tends to go down. So there's an example of a negative correlation. Now our next step here is our best fit line. Right, so there's our best fit line. So we can see that there seems to be an association there. So first of all, when we do our calculations with Pearson's R value, is it going to be a negative number or a positive number? It's going to be a negative number. Is it going to be closer to 0.5 or 0.9? And I don't know. 0.9 is very tight, right? 0.9 is very close to the closer it is to 1, the better the association is. Does this really look like a 0.9? Let's give it a try. Analyze, correlate. I mean, you know, I shouldn't prejudge, right? Okay, poverty rate and high school graduation rate. Click OK and see what our calculation comes out. It comes out, well, it's in between, right? 0.635. It's a negative number. I can't make it bigger. It's -635, which tells us it's a negative correlation. As one goes up, the other goes down. As the high school graduation rate goes up, the poverty rate goes down. Okay, and again, correlation, we're not saying one causes the other, just that there's an association between the two. Could be many, many other reasons for that, right? And can I reject the null hypothesis that this result is due to chance? My null hypothesis is that the Pearson's R value is equal to 0, R equals 0, not 0.65, but 0. And my alternative hypothesis is that it does not equal 0. Can I reject the idea that it's equal to 0? Well, in order to reject the idea that it's equal to 0, I have to be at least I have to have less than 5% chance that we'd get this extreme of value if the null hypothesis were true. And what I wound up with was 0.000, really less than 0.001 chance that this would be that we would get this result if the null hypothesis were true. So therefore, again, 0.000 tells me I can reject the null hypothesis and say that there is a correlation between high school graduation rate and the poverty rate in the 50 states when I examine the 50 states. That's correlation. Next time, we're going to get into regression. In regression, we actually try and see if we can quantify this relationship and use it usefully. So for instance, you notice that it created a formula here, which represents the formula for this straight line. We want to know if we can't create a formula that'll help us, that if we see a person's PSA count, what is the likelihood that they have cancer? Or if we see that that the poverty rate of a community is such and such, or the high school graduation rate of a community is such and such, what's the probability that they have a high poverty rate? So we can use this information to be predictive as well, okay? And to understand what we can do to change things. So in other words, if we see that there's a high association between high school graduation rate and poverty, but only a very weak or no association between poverty and, say, a single parent household, then maybe we could focus our efforts into encouraging higher graduation rates, as opposed to spending money on more support for single parent households. Or maybe it's the other way around, that the percentage of single parent households is even more important, is even more of a correlation with the poverty rate, which it probably is. Let's give that a try. Analyze. Correlate, bivariate. And now I'm going to move high school out of here. I'm going to move single parent household, percentage of single parent households in here. I'm going to click OK. Let's see what our correlation looks like. Well, the correlation is 0.5453. So it's also significant, but the correlation is not as strong. So it looks like high school graduation rate has more of an impact on poverty than the percentage of single family households. We're kind of comparing apples and oranges, kind of, but I mean, just to give you an idea of what kind of thing we might be looking for here. And these correlations, they may be tools that you can use in deciding how to allocate funds, how to determine where you're going to do interventions to reduce poverty, reduce crime rates, and so on and so forth. So that's the idea behind this. We want to get this information, we want to compare these numbers, these variables, these two numerical variables, or 3 or 4 numerical variables. We want to compare them so we get a better understanding of how they are associated and where our efforts are best focused on using them to alter one of the other ones. So reducing poverty by attacking some of the other things that we were able to measure here. So that's basically where I think that's a good spot for us to, break off for now. What I suggest you do though is that in this same section of Blackboard, hang on a second. Let me go to Blackboard again. Okay. So in this same section, you'll see that there is a PowerPoint presentation and a lecture on correlation and regression. Okay, Levi should start talking any second now. I don't have my sound turned down. Okay, I got that.
Actually, so we can go based on, and the other one is the independent or the predictor variable.
Okay, and he goes through a PowerPoint of
one merge row and then each one. Full asset supplementation.
And some examples of correlation. So you can do that with remaining time today, or you can do it later on, right? And what I would suggest you do is he starts off talking about correlation and then kind of folds over into regression. It goes on to regression. Stop at the point where he finishes with correlation and starts to work on regression. And we will cover that on Wednesday. We'll pick that up on Wednesday. Okay? So you guys online, if you want, spend the remaining time rather than, going out and playing and stuff like that. Spend the remaining time watching the first first 30 minutes or so of this presentation here. As a matter of fact, right there, you can see
correlation coefficient is
discusses how that correlation coefficient is actually calculated. I'm not expecting you to know that on an exam, only to figure out how to use SPSS, how to calculate it. But I mean, you should get exposed to this. You should take a look at this as well.